Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new, exciting video. All math-based, of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Why don't you step out inside and let's go to section 6.6 of the Big Ideas Math Integrated Math 2 textbook, Indirect Proof and Proofs, plural, and Inequalities in One Triangle. Let's get right to it. If you want to find other things with this, go to the description section down below, see what we got. I don't know for graphing, but if so, get ready for some graph paper as the PDF or the PDF for this one, which you can, of course, print out or follow along with your own textbook and timestamps down below, along with the entire IM2 playlist. Let's go to war. Let's look at what we're going to talk about. New core vocabularies, indirect proof. Previous things are on proof and inequality. Honestly, I forget what indirect proofs are as a whole thing, so your guess is as good as mine. I'm learning with you. Write indirect proofs, list sides and angles of a triangle in order by size. This is the inequality part. I know this very well. List sides and angles of a triangle in order by size and use the triangle inequality theorem to find possible side lengths of triangles. Because here's the thing. You can't make any old triangle from any three side lengths. There need to be certain sizes by comparison, which we're going to look at with the theorem. Let's learn together about indirect proofs, or let me see what it is again. Suppose a student looks around a cafeteria, concludes that hamburgers are not being served, and explains as follows. At first, I assumed we are having hamburgers because today is Tuesday, and Tuesday is usually hamburger day. There is always ketchup on the table when we have hamburgers, so I looked for the ketchup and I didn't see any. So my assumption is we're not having hamburgers must be false. The student uses indirect reasoning. In an indirect proof, you start by making the temporary assumption the desired conclusion is false. I don't know if I ever did these. In life, yes, we use this logic and argument stuff all the time. So assumption that the desired conclusion is false. They're assuming, making the temporary assumption, okay. Then by showing this assumption leads to a logical impossibility, you prove the original statement true by contradiction. At first I assumed we're having it, and Tuesday's usually hamburger day. My assumption that we're having it is false. Isn't that the other way around? I'll keep taking a look at more. So how to write an indirect proof, proof by contradiction. Let's practice this a little bit. Step 1, identify the statement you want to prove. Assume temporarily the statement is false by assuming that its opposite is true. Okay? Reason, hopefully they help us a little bit on a scenario. Otherwise, I don't know what I'm going to say. Reason logically until you reach a contradiction. Point out the desired conclusion must be true because the contradiction proves the temporary assumption is false. Now, clearly that wasn't a math one, but that's the idea, right? So use logic as best as possible with the math that you understand and work it out. And it might take some time to do so. So let's see them do a few. I'm kind of learning as I go with this one as well. And I don't know, well, this might lead into the triangle inequality theorem, actually, which would be kind of nice. So writing an indirect proof, let's take a look at one. Write an indirect proof that in a given triangle, there can be at most one right angle. Okay, so let me think about that. So assuming that it's false first, is that what they're saying? So prove it can have it says at most one right angle. Okay, so I want to look at a scenario where it has two right angles. Okay, so here's how I'm going to say it. I want to assume that it has two right angles. Well, if it has two right angles, then those are both 90-degree angles, and both of those would add to 180. But a triangle's interior angle measurement should be 180 in total, and you can't have a third angle that is 0 degrees or negative. Therefore, that cannot be true, and a triangle must only then therefore be able to have at most one right angle. It doesn't have to, but at most. Same with an obtuse angle. I've mentioned that kind of stuff before. So let's see. Assume temporarily, yes, that it has two right angles. Then assume A and B are right angles. They both equal 90. They add to 180. They're showing a little more of the math. They're saying the measure of angle C would have to be 0 afterward, and a triangle can't have 0 degrees. So the exact same thing. Okay, that makes a lot more sense. I don't see where the first one starts off, though, with, I guess this is the final conclusion that it must be false. It was just weird because they said false here, but this part says kind of true. I was a little confused. Sorry about that. I'm working with it. Maybe I should practice this. An indirect proof a scaling triangle cannot have two congruent angles. Well, we're going to learn some more things about it, but in a scaling triangle, all sides must be unique and different. And what we're going to learn in this section, see, this is what I'm curious about, because I think we're going to learn it in this section or whatever, but an isosceles triangle would have congruent angles, and therefore opposite sides would be congruent, but you can't have congruent sides here. Therefore, you can't have congruent angles. I think it's something like that. I think that's with isosceles triangles for that one. Okay, so that was an indirect proof. We'll see how often we do those, and if we do, expect me to type some things out. Relating side, oh, here it is. Relating side length and angle measure. So here's the part that I wanted to kind of get into with the equal sides and equal measure. Drawn a two-scaling triangle. Okay, boom. Find the largest angle and longest side and mark them in red. Find the smallest angle and shortest side and mark them in blue. What do you notice? So what we notice is opposite the largest angle is the longest side. Opposite the smallest angle is the shortest side. And there's very much truth to that. It's always true in that way. It's not a direct proportion in some sort of way, like twice the angle. If you double the angle, that it doubles the side. Nothing like that. No, there's trigonometry that would show otherwise and how you do that. But that's the relationship that they're talking about here. So this is the relationships in example 2 are true for all triangles as stated in the two theorems below. Okay? These relationships can help you decide whether a particular arrangement of side lengths and angle measures in a triangle may be possible. So keep in mind that opposite the largest side must be the largest angle. That's the larger angle theorem. Let's go with that one first. If one angle of a triangle is larger than another angle, then the side opposite the larger angle is longest than the side opposite the smaller angle. So opposite the 50-degree angle must be a longer side than the side opposite the 30-degree angle. And B, we could also actually figure out, by the way, that B is going to be 100 degrees, so the opposite that would be the longest side too. Okay, longer side theorem. I don't know why I didn't do this one first. Opposite the longer side is a larger angle as well. Opposite this side length 8 is going to be an angle C that's bigger than opposite side length 5, which is going to have a smaller angle A measure. Okay. And so that goes to that one I was just doing before with the previous example. If you have a scalene triangle with congruent angles, opposite congruent angles would be congruent sides. That's what an isosceles triangle does. That's what I was saying. We got to learn that at some point first. So interesting. All right, so let's do an indirect proof of measure of angle A is greater than measure of angle C. So this is bigger than this. Let's prove that BC is greater than AB with indirect proof stuff. So let's assume the false thing. They say assume that BC is not greater than AB. Then it follows either that it's less than it or it's equal than it. If it's less than it, then A would be less than C. A would be smaller by the triangle longer side theorem. I'm not going to know that name. Let me see them. Triangle longer side and larger angle. Okay. Triangle longer side theorem. If BC was equal, then they would be equal by the base angles theorem, or like how isosceles triangles would work. Both conclusions contradict the given statement here, so the temporary thing cannot be true. This proves it. So you're really going to have to go off the beaten path on some of these and go like, let's dispute the proof by, or excuse me, let's go off a false assumption of the theorem by doing another version of the theorem over here. Oh, I see. This was the larger angle theorem, and then they used the longer side theorem, base angles theorem. I guess if you don't use the same theorem in your proof, then you're good. That's good. Okay, let's keep going, and let's see what other... If this is a lot of indirect proofs, guys, we're going to be in trouble, meaning it's going to be a long one, and I have to think about them. Ordering angle measures of a triangle. You're constructing a stage prop that shows a large triangular mountain. The bottom edge of the mountain is about 32 feet long. Ooh, oh, they have it measured down here. So 32 feet long. The left slope is about 24 feet long, and the right slope is about 26 feet long. List the angles of triangle JKL in order from smallest to largest. So let's just get this out of the way because it's not really an indirect proof thing. Opposite the largest side is the largest angle. The longest side is the largest angle. So opposite 32 is measure of angle K. That's the largest. Opposite 24 is measure of angle L. That's the smallest. So when they order them, angle L is the smallest, J is the middle, and K is the largest because of that. 26 is in the middle. Side lengths of a triangle is going to be the same but opposite. And here's the interesting thing about this one. They don't have to give you all three angles. They can give you just two of them. And because the interior angle sum of a triangle is 180, you can see they calculate the third angle right here. So this one would be 82 degrees. So opposite the largest angle is the longest side. So 82. Opposite that is length DE. That's the longest. Opposite 47 degrees would be the smallest. So DF is the smallest. So DF is the small segment. EF is in the middle. And DE is the largest there. All right, we'll do more practice later, unless it's indirect proof stuff. I might have to practice that with you. All right, next one's the triangle inequality theorem. And I don't know if they're kind of using a compass thing with this as well, showing you the arcs. This is perfect. Perfect enough. Not every group of three segments can be used to form a triangle. It's kind of what I was saying. The lengths of the segments must fit a certain relationship. For example, 3 attempted triangle constructions using segments with given lengths are shown below. Only the first group of segments forms a triangle. So if you notice, what they're doing here is just by construction, they're kind of showing this length is 4, whether I bend it up here, down here, or right there. Wherever I bend it, this is all 4, and this is 2 based on a bend here. When they bend at a certain length there, they can actually close and connect to make a triangle. With this side length being 5, that's the important thing. If it was too long, then they probably couldn't reach each other. Case in point, look at this side length 5, and these are each 2. Well, 2 plus 2 is 4, so 4 isn't greater than 5. It's not equal to 5. It's less than 5. It can't reach. They can't reach and connect. They're like, going like that. No matter how much they bend, no matter how closely they bend here, and this is the longest they can go, when you flatten out completely, they still can't reach and connect with each other. And then you have this one where 3 and 2, if you went all the way down to the bottom where they laid flat, and this was 2 and this was 3, they would actually connect. But they're no longer a triangle. So the more you bend up, the farther apart they'd go. The more you swing down, the closer they'd get. But if they connect right at the end, they're no longer a triangle. So what is this inequality theorem that we're talking about here? Well, the sum of the lengths of any 2 sides of a triangle is greater than the length of the third side. To be a triangle, one side length plus another side length must be greater than any third side length, the third side length. Normally, you really want to compare the 2 shorter ones and add them up and make sure they're greater than the third, and that's kind of a scenario that we're looking at right there. But all 3 have to apply, obviously, because you don't know which one's shortest and longest. And obviously, a longer one plus this one, of course, will be greater than this one already, because they're already longer. But the 2 smaller ones have to add up and be greater than the third. They can't be equal, and they clearly can't be less as well. Excuse me. Now they start talking about finding possible side lengths. Let's say that you know the length's 14. I gotta drink water. All right, here we go. Here we have a triangle side length 14 and one of 9, and we're trying to figure out what values of x can qualify here. So what they do, they establish that 14 is already longer than 9. We don't know how big x quite is yet, or how big x can be, and of course there would be some sort of limit when it comes to this thing. But 14 being larger than 9 means 9 should never need to compare as the biggest number in here. But x can be as small as something or as large as something. How small or how large can it be? Let's first look at small values of x, meaning let's add x with 9 and make sure it's greater than 14. So we set up an inequality that says these 2 have to add up to become greater than that side, assuming 14 is the largest. Subtract 9 from both sides and x has to be greater than 5. As long as x is greater than 5, then you can make a triangle out of it. If x is 5, they only reach at the bottom where it flattens out. If x is less than 5, they don't ever connect at all. So it's never a triangle unless x is greater than 5. But can it be anything greater than 5? Not quite, because what if x is that longest side? What if x was 100? Well, 9 plus 14 ain't greater than 100, right? We need to make sure that x is within the 9 plus 14 range. So now, assume 9 and 14 are the 2 shortest sides, and x is the longest here. 9 plus 14 is 23. 23 is to be greater than x, or plainly put, x be less than 23. So x has to be somewhere between 5 and 23. It can't be 23 and it can't be 5. It can be 5.1, it can be 22.9, and it can be 10, and something like that. Now, notice that they never did one, and I was kind of bringing this up. Notice they never did x plus 14 is greater than 9, because this would say x is greater than negative 5. I mean, not only can x not be negative numbers to qualify here, but with x being larger than 5 already, it already hit our bottom, and this can't be our bottom. Remember, 9 cannot be the longest side if 14 is there, so there's no reason to make that comparison. It doesn't really make sense to do. Okay, monitoring progress. If it's not an indirect proof, I'm going to leave it. Okay, so that's the lecture portion, guys. We're going to work into this stuff. I don't know how the indirect proofs are going to go. I need to practice it. Honestly, I don't think I ever did them in math before, so you and me together, we're going to get to those. Let's first start with the vocabulary and core concept check. Why is an indirect proof also called a proof by contradiction? Because you assume something's true until it doesn't work. You assume the opposite of something is true until it breaks. Or something along the line, basically, right? You look at the false version of something. I think it's kind of how they say it. You look at the false version of something, and then you kind of work on that thing. And that's the thing on the, I like to do the fire trucks are red thing. In some cases, I like to really just make the assumption that all fire trucks really are red. But I'm trying to think how I would work that. Or say all fire trucks are not red. First, I go with the assumption that all fire trucks are red, and then I go and find a blue fire truck, and then I say therefore it's not. That's a proof by contradiction. Once you find some case where it breaks, you're good. All right, how can you tell which side of a triangle is the longest from the angle measures of the triangle? How can you tell which side is the shortest? So I kind of said this one a few times here. We're going to say opposite the, what are they saying? Longest side. Which side of a triangle is the longest side? Opposite the largest side is the longest angle. And then opposite the shortest side is the smallest angle. Point blank, end of story. That's it. Okay. I'm nervous about my indirect proof practice here. We'll see what we do. I hope I'm helpful for you. That's the important part. And of course, I'll learn as I go. And we'll see if I even end up teaching this to my students. I'm just doing this next part of the video. Numbers 3 through, I think, 47. 49. All right, let's go ahead and take a look. We do start off with indirect proofs. They just say the first step. In exercises 3 through 6, write the first step in an indirect proof of the statement. Now, what I'm also curious about is what kinds of questions they give us. Is this all about this current chapter only, or will they talk about, oh, a parallelogram, and oh, a circle, and I don't know. We're going to figure out what they're going to do. So that step 1 is the assume it's not true kind of thing. Let me see how it is. If WV plus VU does not equal 12 inches and VU equals 5 inches, then WV cannot equal 7 inches. Okay, I got to think of this step 1 here. So the step 1, we'd have to say then, let's assume that WV plus VU does equal 12. Where's the if? Maybe we say... Wait, hold on. I actually got to go back already. Are we showing the last part? I think we go to the last part. So step 1 is going to be, in this case, assume that WV equals 7 inches. So you're just changing the conclusion part around. I think I'm understanding what I need to do more for the contradiction part. Changing the conclusion part. So if x and y, and we're not doing the full thing, but if x and y are odd integers, then xy is odd. So in step 1 here, we're assuming that xy, now by the way, xy means x times y. Xy is even. So assume that it's even. Now I have 2 odd numbers that I multiply, and then I find out that I get an odd number, therefore it can't be even, therefore it's odd. Okay, so yeah, it's working. All right, number 5, in triangle ABC, if measure of A is angle A is 100 degrees, then angle B is not a right angle. Honestly, I'm pretty new at these. I'm sure you are as well. So step 1 here is we want to assume that the angle B, I don't know if I have that symbol. I think I do somewhere. No, I don't think I have the symbol. So I'm going to have to use kind of a less than B. Assume angle B is a right angle. And then you find out that that doesn't work. That's, yeah, I want to keep going on these things. All we're doing is step 1, though. It's just a really quick practice. So I probably shouldn't overthink these. Just change this last part. That's literally all you're doing. I want to keep going forward, and I keep telling myself to stop. So I really, all right. In triangle JKL, if M is the midpoint of KL, then segment JM is a median. That's right. Oh, yeah, duh. We have to look at that. I'm like, that's true. Okay, so step 1, assume JM is not a median. All right, so yeah, that's literally, guys, all you're practicing there. We'll see what we're going to do with it later. So sorry if I spent longer on that than I should have. I just wanted to make sure that I'm understanding what they want to do with these in full. We probably get to do some more of these with logic and stuff later. I'll do a lot better once we hit like 11. All right, next exercise is 7 and 8. Determine which 2 statements contradict each other. Explain your reasoning. So triangle LMN is a right triangle. Angle L is congruent to angle N, and triangle LMN is equilateral. So which one contradict each other? Well, A contradicts with C. So here's the thing. In triangle LMN, you could have M be the right angle. Excuse me, while L and N could be still congruent to each other. They could be two 45-degree angles. Meanwhile, in triangle LMN is equilateral. All of them have to be congruent right here. So it says which ones contradict each other. It's not which ones must be true together. It's which ones could be true together. These could not be true together. You couldn't have an equilateral triangle be a right triangle simply because, so I'm just going to put A and C. A and C. All angles in an equilateral triangle must be 60 degrees. Whereas a right triangle has a 90-degree angle. That's it. I don't think we have to explain why the other one works, even though I did to you that you could have a right triangle with congruent angles. They never mentioned that L or N has to be the congruent angles there. Number 8. Both angle X and angle Y have measures greater than 20 degrees, okay? Both angle X and angle Y have measures less than 30 degrees. Well, those are both entirely possible. You could have a 25-degree angle, which is fine. Measure of angle X plus measure of angle Y equals 62 degrees. Now, it doesn't say equals. It doesn't say X is 62 and Y is 62. They add to 62. So think about things that have to add to 62 here. You could have a... So you could obviously have a 61-degree angle and a 1-degree angle where, they have to be greater than or less than. Well, not necessarily. Okay, they couldn't both be less than. They couldn't both be less than, right? Because if they were both less than 30 degrees, then you'd be looking at a sum that's less than 60 degrees. So B and C, if both angles were less than 30 degrees, then their sum would be less than 60 degrees. And therefore cannot be 62 degrees. Okay. Now, they don't have to both be more than 20 degrees, but that doesn't contradict this statement that they can add and still equal 62 degrees. So that's the point. It's could versus must, and these are just could scenarios that we need. In exercises 9 and 10, use a ruler and protractor to draw the given type of triangle. Mark the largest angle and longest side in red and the smallest angle and shortest side in blue. What do you notice? Okay, let's whip out our protractors and stuff. All right, use a ruler and protractor to draw the given type. So an acute scalene triangle. So if I use the ruler, I don't know which one I want to do first here. Mark the largest angle, longest side in red. I don't know, guys. I'm gonna make a triangle, and then I'll measure it afterward. I'm not gonna, because I can't use both tools at once, if that makes sense. So with this one here, I'm gonna go like that. This looks pretty. Oh, it needs to be acute. Maybe I need it. Acute and yet scalene. Is that still acute? I think that's acute, and it appears scalene as well. It's kind of hard to do scalene with acute because they all need to be less than 60, which means some could get pretty close to 60 altogether. Couldn't I don't know. Because I can't make any of them obtuse, but I guess that's going to be good enough there. Maybe I can grow it or something like that. Sorry about that. I gotta think about how I need to construct my own thing. You could probably do it with the ruler and protractor pretty fast there. All right, so my ruler tool, I got this guy. Ta-da! Cha! And now I need to play some rotation stuff. This is the stuff that's really hard on my end because, that's about 5 inches right there. Perfect. This is just a lot harder on my end than anything else. So I got a 5-inch side. And then, I didn't measure these out. I believe that's the shortest side. I just got to think about what the shortest angle is. I don't really know. Actually, this one might be the shortest here. Nope, that's about 5.5. These are pretty good measurements. 5.5 inches. 5.5 inches there. Let's hope that this one kind of looks pretty good as well. I don't like that they say, what do you notice? We already have the theorem in place. Look at that. That's like 6 inches. All right, pretty cool. At least I know it's scalene. And those, I'm glad I didn't have to go to like measurement school and go to 16ths. I will have to probably on the next one. We'll find out. Maybe we can just copy these ones somehow. Now let's do the protractor. Let's go to my protractor tool, which looks like this massive hunk of something that I can shrink. So I gotta lay this, I gotta rest this against one of these guys here. Like that. And don't worry, I'll mark the sides and stuff in a second. Now, I don't know if they actually require that I do all this kind of stuff, but I will. So I got a 71 degree angle here. I'll just go ahead and put it there for now because otherwise I'll forget to write it. Here I got... Sorry about this. Because yours is possibly totally different, right? This is an open-ended kind of question here. Then I got this one, which is about... Did that mark? 51 degrees. Sorry that it's kind of like that. Now, I'm going to go ahead and just put those two in. I need not measure the third one because it should just, they should add to 180. So 71 plus 51 is 122, and 180 minus 122 is 58. So I got a 58 degree angle there. So 71, 51, and 58. Okay, mark things in red and blue. Let me just change those and call those 71 and 51. 71 degrees, 51 degrees. Okay, mark this largest angle and longest side in red. All right, largest angle here. Longest side is this one. Okay. Mark the smallest angle and shortest side in blue. Smallest angle and shortest side. What do I notice? Opposite the largest side is the longest side is the largest angle, and opposite the smallest side is the shortest. I can't say this. Opposite the longest side is the largest angle, and opposite the shortest side is the smallest angle. I mean, that's the same thing as our number 2 thing, and number 10 will have the exact same answer as this one because that's just how these triangles work. So there's number 9. Let's go and do number 10 in the same fashion. This is part of the video that if you like to skip, go ahead. And I wish I was talking to myself when I said that. I don't know how much you're learning off this here. A right scalene triangle. Well, as long as the legs are different, the hypotenuse will be different than the legs. So I'm just going to go ahead and work off that. And let's just hope that these inches do something that kind of is all right with me. Because they probably won't. Oh, I wasn't using inches before. I was using centimeters. Maybe that's why it was so good. Let me go back to this thing. I mean, here's the thing. What am I measuring, really, at the end of the day? Because this is on your screen, and your screen can be whatever it is. Same with my screen. I don't know that these are measured exactly to something. But let's see. At least this will help me with decimal knowledge here, because this one's not perfect anymore. So this one's about 3.8 centimeters, but at least I can work in those kinds of decimals by tens. One good thing about the metric system. Powers of 10. This one measures to about 8.3 centimeters. Now, I could use Pythagorean theorem here and determine that third side, but because these are just approximations, I'll just let it be what it is. Let's just rotate into this one and figure it out. It's going to be about 7.4 centimeters. All right, we know we have a 90 degree angle here. Let's figure out one of the other ones, and then by default, we'll kind of know what that other one is, because we can just subtract it really from 90, not even have to do it from 180. So, oh, I forgot I could do that. I have 2 different things. I have to rotate the actual protractor itself. So that's going to be oh. Hold on. Sorry about this. All right. I think it's about as close as I can get there. So what is that? Oh, let's ground this. Boom. So what is that angle, you ask? Doesn't tell me. 332 degrees. Oh, I must have these things backwards. But then that must mean it's, what, 28 degree? 28 degrees, I think, then? Is that answer? So let's see. Yeah, 28 degrees. Okay, so this guy's 28 degrees right there. Looks like this smallest angle. And 90 minus 28 is 62. So this is going to be 62 degrees. Okay, here is the largest angle. Here is the longest side. Here is the smallest angle. Here is the shortest side. What do I notice? Well, let me copy and paste this. There you go. Opposite the longest side is the largest angle. Opposite the shortest side is the smallest angle. I'm sorry, that was number 10. I was so into what I was doing, I forgot to change that. All right, let's get to what I want to talk about. Exercises 11 and 12 list the angles of the given triangle from smallest to largest. You're just listing the angles here. So based on this drawing that we have, where we copy and paste that. You know, I don't know if I'm going to be copy and paste this very often. I just want to kind of bring this up. Remember, we're talking opposite, longest side is largest angle, opposite, shortest side is smallest angle, like that. So angle S says smallest to largest. Angle S is going to be the smallest. Angle R is the one in the middle. Angle R is the next, and then angle T is the largest there. That's how we're going to work that. Yeah, I'll just go based off. I'm not going to copy down the diagram per se, just it's based off what we have there, because we can tell based off what the side lengths are. Number 12, opposite the 13. Opposite the 13 should be the smallest angle J. So we have angle J first. And then opposite JL should be angle K. Angle K. And I don't want to say go by the drawing, and also don't assume this is a right angle or anything like that, but the drawing does seem to match up with what it is. And then opposite 28 is angle L, which is the largest one, angle L. All right, next side is 13 to 16. List the sides of the given triangle from shortest to largest. So now, based off these ones, we have the angle measures, and opposite the smallest angle is the shortest side. Opposite the largest angle is the longest side. So 51 is the smallest angle. So segment AB will be the shortest side here, segment AB. And then opposite the 62 degree angle A will be segment BC. And then last but not least, we have segment AC opposite the 67 degree largest angle there. So AC, like that. Number 14. 32 is the smallest angle, so we're going to do XY first. And then opposite 36, we're going to have YZ. And opposite angle Y, we're going to have XZ. So we're going to say XY, XY, YZ, and then XZ. Now, number 15, we're missing an angle measure here. So on number 15, what we have to do is find that third angle measure. Now, it's going to be the sum of these angles add to 180. So the measure of angle M plus 127 plus 29 equals 180. Let's add 127 with 29, and we get 156. Subtract 156 from both sides. The measure of angle M is going to give you 24 degrees. So if I write that in there, that might help you with what we're going to be doing off of that, because it looks like 24 is the smallest angle. So 24 degrees is the smallest angle. Opposite that will be the shortest side, segment length NP. And then opposite the 29 is segment length MN right there. And then last but not least, we have MP opposite the 127. So MN comes next, and then MP. So there's the final answer, number 15. Now, number 16 is a lot like number 15, only we have one angle measure. But just like that one problem, I don't know if you got to do the problem, but just like the problem I just did, this is a 90-degree angle, which is something we probably should write down. But on top of that, we don't have to add all of these to 180. The G and D are complementary angles. If this is 90, then these have to add to 90 because they all have to add to 180. So don't go too far into needing to add everything here, but it's good to list that 90 to compare to these. Here's the thing. The right angle is going to have to be the largest in a triangle, so we already know that one's the largest. But these two would just add to 90. If you subtract 33 from both sides, you're going to get 57 degrees here. 57. So there's D at 57 degrees. So we're going from shortest to longest. Opposite the 33 is going to be the shortest. That's side length FD. In a right triangle, guys, the hypotenuse is the longest, period. And I'm sure there's going to be some sort of indirect proof thing about that. Argue that the hypotenuse is the longest side or something. First, we say it's not the longest side. So FD and then FG. FG opposite the 57 and opposite the 90 is DG. The hypotenuse. That's number 16. All right, 17 to 20. Let's go at it. Describe the possible lengths of the third side of the triangle given the lengths of the other two sides. So on number 17 here, we have a 5-inch side and a 12-inch side. So here's the concept, and I won't draw it each time here, but we can have one consideration where you have the 5 and 12-inch sides here, and then X is just this third side. And what if 12 was the longest side? I mean, I kind of drew it to make it as such here, but what if 12 was the longest side? X can be, I don't know, we'll see. What we're going to do is use the triangle inequality theorem, and what we state here is that X plus 5 has to be greater than 12. Period. The two sides of a triangle must add to be greater than the third side. So if I subtract 5 from both sides here, you'll see that X has to be greater than 7 inches. Make sure I at least put the inches for that guy, and I'll keep going as far as what I write. So X has to be greater than 7 inches. Any smaller and you couldn't make a triangle out of it. It just wouldn't be. Even 7. 7's not enough. Now, the second case that we want to do, and I kind of want to draw this next to it, so let me think on that. Let me move this down. And let me just do a second. Normally, I won't draw that thing. I'm just going to do my two cases. The next one is consider the case where X is the longest side. So now you have the 5 and the 12. And the drawing is just to help encapsulate this idea that for 5 and 12 to connect, they have to be longer than X when added together. 5 plus 12 has to be greater than X. So X has to be greater than 17. Excuse me, less than 17. 17 inches right there. So X has to be greater than 7 but less than 17. I'm going to write it as a compound inequality. Like that. X is somewhere between 7 and 17 inches. There are a lot of different ways you can write it, and that's the one I'm going to go for, and that works out. But you got to do both cases. Notice that I never did one where X plus 12 had to be greater than 5. 12 is already greater than 5. That would lead you to a negative result. The smallest X can be a 7. You don't need to do that one. You just have to just make sure you know these other numbers to compare them to begin with. So I'm not going to draw those other ones after this. Just understand the comparison, how I did it. Let's look at number 18. We got 12 feet. And by the way, notice the units. We got to keep those in consideration. Let's first look at the small case for X, where X plus 12 has to be greater than 18. I mean, these are pretty straightforward problems, guys, as far as what you do. Just make sure you can write the compound inequality at the end and you compare correctly. Subtract 12 and you say X has to be greater than 6 feet. So there's one of them. And then in the other case, 12 plus 18, if they were both the smaller ones, have to be greater than X. So 30 has to be greater than X, or X has to be less than 30 feet. X has to be somewhere between 6 and 30, and we good. 6 feet, X 30 feet. Like that. That's a pretty good range to be between. You can still make a triangle for anything there. That seems to work out pretty nice. This might be an even bigger range. Number 19. Or a smaller range, actually. No, we'll see. Number 19. 2 feet and 40 feet. Okay. So in the small case for X, X plus 2 has to be greater than 40. So subtract 2 from both sides. X has to be greater than 38 feet. Wow. Okay, I forgot. It's going to be a small case here. There's very little wiggle room for what X can be based on the other one being so small. The closer these numbers are together, the more wiggle room X will actually get. I don't know why I didn't think about that. In this other case here, 2 plus 40 has to be greater than X. So now X has to be less than 42, as 42 has to be greater than X, 42 feet. So yeah, this is actually a small range here. X has to be somewhere between 38 feet. My F's aren't really showing up here. And 42 feet, like that. Very, very small range. Not very, very much we can do with it. Now, number 20, this kind of goes to that other thing that I was saying here, the 25 meters thing. Excuse me, with them being the same, I said the closer they are together, the more the X can change. Let's do 25 meters and 25 meters. Okay, so in this case here, consider x to be one of the 25 meter, or excuse me, one of the sides along 25. X plus 25 has to be greater than 25. If you subtract that, that means x has to be greater than 0. And that's true in all cases. X needs to be positive, but this is especially true here. As long as x has any tiny length whatsoever, you can have the smallest of, you can have a 25 meter thing here and a 25 meter thing here and be super easy small, like 25 and 25. As long as x is just a little bit, then we can still make a triangle out of it and it's good. Now, what if the 25 is expanded so far, like this and like this, x can be this very long thing, but how long can it get? Well, the 25s, 25 plus 25 being greater than x, which must be true, 50. X has to be less than 50 feet. Oh, meters. Excuse me, in this case. Sorry if I was saying feet. So x is anywhere between 0 and 50 meters, and we are golden. It can even be 25 meters, like the other one. It can make an equilateral triangle. All right. In 21 and 24, is it possible to construct a triangle with the given side lengths? If not, explain why not. The only test we have to check in any of these ones that I can think about is check the two smallest sides and add them up. If they are greater than the third side, the longest side, then you're good. 6 plus 7 is greater than 11. So yes. Excuse me. Let's get to there. Yes. 13 is greater than 11, so yes. Let me copy down the problem too. Excuse me. I really should be doing that. 6, 7, and 11. Let me kind of put the yes a little bit lower there. All right. Yes. As long as the sum of two sides, any two sides is greater than the third, the true one to check are the two smallest sides, because clearly if the third side is included, the longest side is included in any of the other sums, of course it would be greater than the other ones. But for all sides of the triangle, this has to work. Excuse me. 3, 6, 9. 3 plus 6 greater than 9. Well, you have 9 greater than 9. Not the case. Let's put a question mark first and then kind of get to the no. Not a true statement. So no, you cannot make a triangle out of side lengths 3, 6, and 9. 28, 17, and 46. Number 23. 28, 17, and 46. Go with the 28 and 17. Add those two. 28 plus 17. Is it greater than 46? 28 plus 17 is 45. 45 ain't greater than 46. So a resounding no. And then lastly on number 24, we have 35, 120, and 125. 35, 120, 125. I always say this, but I feel like we're going pretty good on time right here, and then it's gonna slow up. Probably right after this. 35 plus 120, is it greater than 125? You betcha. That's 155, which is greater than 125. So yes, you can make a triangle out of that. You can make many, actually, just one. Error analysis. Describe and correct the error in writing the first step of an indirect proof. I don't know. This isn't my forte, but let's see where they made this mistake. Show that angle A is obtuse and assume temporarily that angle A is acute. Okay. The problem with this one is there are other kinds of angles that you can do. Just because an angle is not obtuse doesn't necessarily mean that it is acute. It could also be a right angle. I mean, I don't know if they're talking about triangles, but it could also be a straight angle. And in some cases, a convex angle. If we're not talking about triangles. Anyway, all we have to do for correction, assume, they say temporarily. I never put that before. I'm sorry. Assume temporarily that angle A is not obtuse. That's all. There's just, it can be anything. Now, who knows what the rest of this thing is going to talk about, right? I don't know what this setup is. But assume that it's not obtuse. Then you speak out about everything that's not that. And I think that works. All right, let's keep moving forward. Number 26, another error analysis question. Describe and correct the error in labeling side lengths 1, 2, and root 3 on the triangle. Now, I'm very familiar with the 1 to 2 to root 3 triangle, and I can tell you this is not the case. So the error here is this, and I can get a little deep into this. Not super, but I can help you out with this. Even if you don't know trig, triangle similarity, and any of that stuff. The problem is, and I'm going to type this, opposite the largest angle should be the largest side. And the square root of 3 is not greater. Square root, oh, that didn't insert. The square root of 3 is not greater than 2. Now, even if you didn't have a calculator to know for sure what the square root of 3 was, because it's an irrational number. I don't know what it is exactly. It's 1.7 something, but I don't know exactly what it is. How's the way that you can know without a calculator? Because here's the thing. If you put these in other places, and you can use Pythagorean theorem. Listen, there are a lot of ways you can do this thing, but the thing I wanted to mention is that 2 is the square root of 4. 2 is the square root of 4. Equals 2 is square root of 4. And square root of 4, I don't know why it doesn't extend the thing out, but that's okay. And square root of 4 is greater than square root of 3. Square root of 3. Therefore, 2 is greater. 2 is greater than, I want to get that down to the bottom. 2 is greater than the square root of 3. Okay. Now, there are a lot of ways you can do this. You can use Pythagorean theorem to determine that, all that kind of stuff. But the 2 should go on the other part here. So as far as labeling the sides go in a 30, 60, 90 triangle, I mean, I'll make up the appearance of a 30, 60, 90. Let's pretend that it's this. But this does go back to my other talk in saying that just because you double an angle measure doesn't mean that you double the side length. That's not true. If this was 60 and this is the right angle and this is 30 right here, this is 1, this is 2, this is square root of 3. You can use Pythagorean theorem to determine that 1 squared plus root 3 squared equals 2 squared. Because this is 4, this is 1 plus 3, and 4 equals 4. That checks out. Anyway, opposite 30 is 1, opposite 60 is the square root of 3. Notice how you double 30 to get 60, but you don't double 1 to get the square root of 3. And that could be a reason why they put that. I don't know. All right. Let's keep going. 27 and 28, we have some form of reasoning. I love this. You are a lawyer representing a client who's been accused of a crime. I like it. It's not even math. It's just logic and reasoning. Let's look at what they're going to say. The crime took place in Los Angeles, California. Security footage shows your client in New York at the time of the crime. Explain how to use indirect reasoning to prove your client is innocent. So, what are we going to say? The crime, accused of a crime. They were accused of being in Los Angeles. Am I saying that right? Security footage shows your client is in New York at the time. To prove your client is innocent. I want to prove innocence. First assume. First, I will temporarily assume. I forgot it's the last statement. Temporarily assume that my client is not innocent. You don't prove innocence. You prove not guilty. So I'm gonna say guilty. First, I will temporarily assume my client is guilty. I don't think you want to say that in court because suddenly they're like, aha, you admit that they're guilty. This is kind of fun. If my client is guilty, then that means, this is fun, that they never say he, so that my client would have been in Los Angeles, California, at the time of the crime. However, and I think this is step 3. I think the however is the dispute. However, security footage, I like this. Security footage shows, as long as it's not math, right? Your client, my client. Security shows my client is in New York at the time of the crime. I think I can just do the therefore here. Therefore, my client is innocent. He hired the man who committed the crime. I think that's how I write the steps. I'm going with that. Let me check. I'll entertain you with my face. Let me check on how the other ones were handled with the last part. Oh, hold on. Let me change how I wrote it. So I think that part in step 3 does not include the false portion of it. So I'm going back to here. So I want to say this. This part goes here. And then this is just the last part there. I can probably say more at the end. But that part goes in step 2. Kind of a big step 2. All right, number 28. Your class has fewer than 30 students. The teacher divides your class into 2 groups. The first group has 15 students. Use indirect reasoning to show the second group must have fewer than 15 students. So remember, the class doesn't have 30 students. It has fewer than 30 students. So let's, and I don't know if we say this like first I will, but I'm going to keep saying that. First I will, they use temporarily assume that the second group must not have fewer than 50 students. Must not? Do I just say may? No. I'll say 15 students or more. Must have 15 students or more, because that's the opposite. Because the must not is just going to imply that anyway. So 15 students or more. If I mean this is kind of just math. If I add the first group's 15 students with my group of 15 plus students, I will have a total of 30 plus students. However, my class, I thought my spacing used to be kind of normal. I don't know why this is. Here we go. No, I don't know. That's okay. However, my class has fewer than 30 students, which contradicts the statement. Therefore, I think I have to hit enter to do this. So that's okay. Therefore, the second group must have fewer than 15 students. Isn't the math one more boring than the court one? I could have been a lawyer. Instead, I'm just making long YouTube videos, man. All right, number 29, problem solving. Indirect proofs come and go, don't they? Number 29. I mean, how many times? I've probably done a lot of indirect proofs before. Like, not written out, but just even talking with you guys. I must use indirect proof logic a lot. Which statement about triangle TUV is false? A, UV is greater than TVU. Let's see. Well, here's UV. I think I said TVU. I meant TU. Here's UV, here's TU. UV must be greater than TU because 84 is more than 48. The side opposite, the larger angle, should be the longer side. So that is a true statement. I'm going to just put a true there. B, UV plus TV has to be greater than TU. Here's UV, here's TV. This has to be greater than TU. That's true for all triangles. As long as we're talking about sides of a triangle, this absolutely must be true. C, UV has to be less than TV. Here's UV, here's TV. We don't know TV's angle opposite, but we can calculate that. That's what we should work on. Let's look at 84. I'm just going to write it over here. 84 plus, and they don't ask us to explain this, and I'm going through explanation. 84 plus 48, which is, sorry, I have to use a mouse on this side of this, 132 degrees. Now, those together, 180 minus 132, I know I'm kind of using student math with that. That's 48 as well. Really? I guess so. So 48 degrees. So 48 degrees there as well. That means that this is the same length as that, but UV, it's all about comparing UV with it. UV being apparently the longest side. UV less than TV? Nah, that ain't going to be the case. UV is definitely going to be longer. So it looks like it's going to be C. Let's look at D. TUV is isosceles. Yeah, that's true. Now that we have this, angle is 48 degrees. Again, base angle is the same. These two are going to be congruent. Absolutely true. So on number 29, which statement about triangle TUV is false? I'm just going to put C. You can kind of see on that side what I did with it. Hopefully be okay that I'm doing that. Unless they ask me to explain it. Problem 30. In triangle RST, which is a possible side length for ST. Select all that apply. Let's figure out angle R before we do anything. Well, I guess we kind of have to figure out angle R because ST is opposite that. So 65 plus 56 is 121 degrees. And 180 minus 121 is 59 degrees. So 59 degrees. Okay, so what's a possible side length for ST? I mean, here's the thing. There is an exact measure that you could figure out using what's called the law of sines. Unfortunately, we don't get to figure that thing out here. So 59 is the in-between angle of these two here, and 8 is opposite the smallest angle. Therefore, 8 has to be the shortest side. Therefore, 7 is just simply not possible. 7 is just simply not possible. 8 is probably closer to what the answer could be, but I don't know for sure. It can't be exactly 8, though, because if this ain't the same, then it's not isosceles. Therefore, it can't be 8. It could be 9 because 9 is more than 8, and so is 10. 10 is more than 8 as well. These could be possible. I don't know what they are. I don't know what the answer is, but, you know, C and D here. And again, they're not really asking me to explain. I'm doing the drawing stuff on that side, and I hope that, once again, you're okay with me showing what that is. As long as it's more than 8, then it's possible. I mean, again, you don't know what it's going to do yet unless you know the law of sines, and I could tell you exactly what it is if I did work it out, but I'm not going to. So these are possible ones just based off that. All right, number 31. Write an indirect proof that an odd number is not divisible by 4. An odd product is not divisible by 4. Okay, so let's see if I got this down. Let's temporarily assume that an odd number is divisible by 4. Oh, come on. I do want to see it divisible by 4. So if it's divisible by 4, now, can I use... Did they say an odd number? Oh my gosh. Can I don't know if I can use an example. Wait, let's assume that it is. Can I just use an example? 5 is an odd number. But that doesn't use all of them. 5 is an odd... I'm going to write this out and see how this works. I don't think that this works, though. No. I don't want to use an example like that. Numbers that are divisible by 4 must be multiples of 4. I'm going to go this way. I don't know if this works completely. Multiples of 4, such as 4, 8, 12, 16, etc., which are all even numbers. This means only even numbers can be divisible by 4. I think that works better. I'm going to say 5 is an odd number. 5 is not divisible by 4, so odd number... No, that doesn't work. Only even numbers can be divisible by 4. Therefore, an odd number is not divisible by 4. Odd numbers can't be even. Right? Okay, I think I like that one the most. Number 32. Write an indirect proof of the statement in triangle QRS if... Hold on. 32. In triangle QRS, if measure of angle Q plus measure of angle R is 90 degrees, measure of angle S is 90 degrees. The only problem with this one for me is going to be the typing format. I can't really use the angle symbol. You're going to have to forgive me for... Here, let me find one online, but I have to copy and paste that every time. So angle symbol text, because I'm very well aware that this thing doesn't really. 8736. 8736. Oh, that didn't work. I was trying to do an alt code, and that didn't really work. Give me a moment. Copy and paste the angle symbol. All right. Let me get an angle symbol. Hey, I got one. All right, I'm going to keep this in my bank right there. And the degree one, is it alt 0167? 0176? There it is. All right, I'm keeping those in my bank, all right? Just let me have those. They're mine. Okay, copy. Write an indirect proof. Now, triangle. Do I have a triangle symbol somewhere? It's weird that I don't have an angle symbol on this thing. I have a triangle symbol here. Let me get this one as well. Okay, I have some symbols in my bank. Just please ignore those for the time being while I write this one out. I want to have fun with these. Okay, indirect proof. Measure of angle S is 90 degrees. Let's temporarily assume. Now, here's the thing for these as well. I should be writing out what they're saying in this statement here. But again, it's on the side. Let's temporarily assume that the measure of angle S is not equal to 90 degrees. There's an unequal thing here. Not equal to 90. I'm just going to use the alt code as I know it. Let's temporarily assume that it's not equal to 90 degrees. Measure of angle Q. Measure of angle Q plus measure of angle R equals 90 degrees, which are two of the three angles of a triangle whose sum must always equal 180 degrees. Okay? I'm going to use what they said before, by the subtraction property of equality. By the subtraction property of equality, measure of angle S must be 90 degrees. I don't know how to get step 2 completed without, I don't know how to write step 3 without that being a part of step 2. Oh, let's assume it's not. I'm sorry. Here, I can't use the subtraction property here. We're gonna add with it. Let me leave out. Hold on. Which are two of the three angles of a triangle. The third angle. When adding measure of angle S. Sorry about this. When adding measure of angle S, you would get a sum that is not equal to 180 degrees, which must always be a triangle's interior angle sum. So, there we go. So, therefore, with that, measure of angle S must be 90 degrees. Let me get rid of those. Let's have to use them again. All right. Number 33. Explain why the hypotenuse of a right triangle must always be longer than either leg. Is this an indirect proof? Doesn't look like it is. So, I kind of mentioned this before. I used the Pythagorean theorem thing, but now that we're talking about this other, the larger angle sum. See, I forget. What do they call it? The largest possible angle theorem? Largest possible side? I forget how they put them. So I don't know if I can use the theorems in my thing unless I come up with it. So the hypotenuse. A hypotenuse only exists in a right triangle. Hypotenuses only exist in right triangles. And are opposite the right angle, which is always the largest angle in its own triangle. By the theorem name, longest, let me look it up. Let me go back to the thing. By the triangle longer side theorem, no, larger angle theorem. One angle is larger. Yeah. By the triangle larger angle theorem. Now I'm back. So by the triangle larger angle theorem, if the right angle is the largest angle in a right triangle, then the hypotenuse will be the longest side. Longer than any leg. I don't really know if I need the first part here specifically, but the whole right angle is, there's only one of them, and it's going to be the largest one. So I think that's going to work it out. All right, number 34. Is it possible to decide if three side lengths form a triangle without checking all three inequalities shown in the triangle inequality theorem? Explain your reasoning. Yes, and that's what I've been doing. And I apologize if I haven't been showing all of them because I don't need to. Possible to decide if three side lengths form a triangle without checking all three. Yes. So, yes, you only really need to check if the two shorter sides add to be larger than the longest side. Third and longest side. This is because the longest side is automatically longer than any other side, even when summed with another side, right? If I already have something that's longer and I just add more to it, it's going to be longer, right? If I'm the richest guy in the world and you pair me up with some other person, poor, rich, whatever, we're still going to, together, we're richer than anybody else because I'm already the richest guy, and things like that. All right, let's keep moving forward. Number 35, modeling with mathematics. You can estimate the width of the river from point A to the tree, at point B by measuring the angle to the tree at several locations along the riverbank. The diagram shows the results for locations C and D. You can estimate the width of the river by measuring the angle to the tree at several locations. So this location C and D. Using triangle BCA, this guy, and triangle BDA, determine the possible widths of the river. Explain your reasoning. So I'm going to bring this diagram over this time so we can play with it a little bit and see what we got. This is number 35, so I'm going to write that down in just a moment. I've had a song playing in my head the entire time I've been recording. I'm not going to tell you which one it is. It's not something that I'd prefer to say. All right, so we have this. Okay, what do they want? Using the triangles to determine the possible widths of the river. So we're trying to figure out what could possibly be here based on what this is. So here's the thing. We have two different triangles, right? These are right angles, by the way. Now this 40 degrees here would mean this is 50 degrees. 50 plus 40 is 90 and all that kind of stuff. And then this is 50 and this is 40. Now that does not mean that these triangles are congruent to each other. You can't prove triangle congruency by angles. They are similar, but they're not necessarily congruent. And I wouldn't make any reason to assume these are congruent in any sort of way because this looks bigger and it will be bigger. Now, from this here, opposite, the 90 is going to be the largest side, but then 50 is next. 50 is next, so 40 is going to be next here. So this side length has to be less than 50. So if this is X, if this is side length X here, X has to be less than 50 yards. I'll explain why if they need me to later. Yeah, so part A. So X has to be less than 50 yards here because it needs to be smaller than the side opposite the larger angle. This is the smallest angle, so it's going to have to be a smaller side as a for sure. However, this being 50 right here needs to be bigger than the side opposite this angle here where the 40 says 35 yards. So X also has to be greater than 35 yards. Therefore, X has to be between 35 yards and 40 yards. How much? 50 yards. How much in between? I don't know. It needs to be in between. I mean, again, we're not using trigonometry to figure this out, although you could. I just explained verbally here, but so in the left triangle, X, the one that I labeled, X must be shorter than the next longest side because it is opposite the shortest angle. And then in this right triangle, X is not the shortest side, not opposite the smallest angle. I said shortest angle here. Let me smallest angle. Not opposite the smallest angle. So it must be greater than the side opposite that angle. I mean, I'm explaining out just kind of what the things are that I said there. And obviously, there's a shorter way you can type that. I don't really know what it is. It's for me to teach you it, not for any other reason. Part B. What could you do if you wanted a closer estimate? Well, you could use trigonometry. Something with the bridge stuff, right? If you wanted a closer estimate, pick a third. That's a good question. Pick distances that are the same. This is a good question. Why am I not coming up with the answer? Come up with the hypotenuse. What could you do if you wanted a closer estimate? You want the angles closer together. Yeah. Oh, okay, yeah. As long as you're able to measure, as long as you're allowed to measure these points, what do they say? Measuring the angle to the tree at several locations along the riverbank. So you'd want to attempt to measure a distance away from point A that is as close to 45 degrees to the tree from some location. This is because, they didn't ask me to explain, but this is because you'd get an isosceles triangle. You would have an isosceles triangle, right triangle, where both legs would ideally be the same length. So yeah, as close as you can to get to 45 degrees. The closer you can get to 45 degrees, the better. Right? Can you get exactly? I don't know. But closer you can get to 45 degrees, the better on that one. Okay, let's go to number 36. Modeling with mathematics. You travel from Fort Peck Lake to Glacier National Park, and from Glacier National Park to Granite Peak. So Fort Peck Lake to Glacier, and Glacier to Granite Peak. Write two inequalities to represent the possible distances from Granite Peak back to Fort Peck Lake. Yeah, how far away are you now as a result of all this wandering and traveling? Because we don't know what these angles are, right? Those weren't measured. All we know is how far we traveled in these straight lines. So x here, if x was added with 489, that would have to, in order to make this a triangle of sorts to go from one to the other, this would have to be greater than 565. We're going to find the shortest possible thing that this was, because ideally could have gone there and kind of straight back. Maybe Granite Peak is right next to Fort Peck Lake. But if I subtract 489 from both sides, don't make me do this math, you get 76 kilometers, I believe. And if 489 plus 565 was greater than x to still maintain that triangle, you could almost be going 565 and then you get another 489. And now you have to go all the way back like that. So pretty much like that. 565 plus 489. I don't know. I'm so bad at this math, guys. I'll be honest. So let's first add the 65 and you get 554. And then add the 500 with that. You get 1,054. I got so bad at math addition, kilometers, by the way. So x is less than 1054 km. I don't know what happened for me to get so bad at it. So anywhere between 76 and 1054 kilometers, that's a large discrepancy. Because, you know, it could be one of those things where you don't know what kind of turn you took to go to that other thing, and you don't have a compass with you, and somehow you landed at the right spot. But, you know, it's like you were blindfolded, spun around 5 times, and then start walking straight in that direction, you'll hit Glacier. Or Granite Peak, but you don't know if you just basically took a straight shot or went right back the way you came or whatever. All right, that's part A. Part B, how is your answer to part A affected if you know that measure of angle 2 is less than measure of angle 1 and measure of angle 2 is less than measure of angle 3? So basically, if measure of angle 2 is the smallest angle, how is your answer to part A affected if measure of angle 2 is the smallest angle, then we know it's not going to be an obtuse angle, which means x is going to be closer. Well, I don't know how close, because how small can an angle be? What's the smallest an angle can be and still be the smallest angle in a triangle? I guess less than 60, right? Less than 60 degrees. Anyway, because we know these other lengths here as well, then we also know how these can compare. If 2 is the smallest, so the thing that we know here is that, I was thinking in stupid terms. Measure of angle 2 is going to, excuse me, not measure of angle 2. If measure of angle 2 is smallest angle, then side opposite is the smallest side. Then x is smallest side. Now, how small can it get? As long as it's less than 489. Therefore, instead of being, sorry about this, x is less than 489 kilometers. So now x is somewhere between 76 and 489. Something like that. Because 489 is the next smallest on here, right? But 2 is the smallest one, so opposite that's going to be the smallest guy. So we've reduced how small it is. I guess it's not that far away. Still pretty far. Even 76 is pretty far, depending on... Hopefully we're not walking. You traveled. I don't know what the traveling is. 37, that looks... Oh, I thought it was like a 3D pyramid. Instead, it's just two angles here. All right, 37. In the figure, segment XY bisects this angle here, WYZ. List all 6 angles of triangle XYZ in WXY in order from smallest to largest. Explain your reasoning. So, okay. These are congruent angles, but they're not part of the same triangle. So even though they're the same angle, they might not necessarily be the biggest angle together or the smallest angle together with what you have. And we do have this length as 15, so we can kind of just tell how things are in general and then how they compare. What they say, list the angles in order from smallest to largest. But these are the same. So wherever they are, they go together. Like rama lama lama da dinga da dinga dong. And we got to call them for what they are as well. We got to use 3 letters quite a bit. I don't have to use 3 letters for W or for Z, but these other ones, I got to call this like WXY and all that. So let me copy and paste this thing over. And let's just try and rank them by putting numbers on them first, and then we can maybe write them out. So in the left triangle, I have, now this is just relative to the triangle, okay? I have 6.4 right here, which is going to be smallest among these, and then 14.1, and then 15, opposite the 15 right there. And in this triangle, opposite the 11.7, I'll have the smallest, and then opposite the 15 is next, and opposite the 15.6 is next right there, next biggest. So here's the thing, though. Notice how within, list all 6 angles from smallest to largest. Notice how within this own triangle itself, this is the largest angle. But then in this triangle, this is the second largest angle, which right now tells me a couple things. Number one, it tells me that angle W is going to be the absolute largest. If I were to order these 1, 2, 3, 4, 5, 6, because these are the same, let's say these are both, 80 degrees, whatever they are, W is going to have to be more than that because it's already bigger than the 2 that are the same, where this is already the biggest one. So angle W is the biggest one. Absolutely. I'd say then, therefore, these would be next, and it doesn't really matter which order that you put them. This is relatively the biggest in its own. I don't know if that really matters, so I'll just call it. Let's say angle XYZ. And then the other one is angle XYW, sure. Now, in the next ones here, the one that I'd say is the smallest is this one right here, this angle X or WXY. Now, the reason for this one is because even though these are both ones, And it's not just that 6.4 is less than 11.7, but it's comparatively less than its other two sides in such a way that, not even just by proportion, but just it's comparatively less than how 11.7 compares to 15 and 15.6 there, which would kind of tell me that that one's absolutely the shortest. And then it's just a matter of these two right here, and this one is going to be smaller than that one, which is smaller than all the rest. So clearly this one's going to be next, angle YXZ. And then this last one's going to be angle Z right there. I did my reasoning with a lot of explaining with you there. I don't know how much I can say with all of that. I'll just kind of list them within here. So comparatively shorter opposite side compared to its sides, right? This one is bigger than... And here's the thing, I think we really needed to know that these were the same in order to get that for sure answer on this one being the biggest. But bigger than 2 of next biggest of known next biggest sides, or biggest angles. Now, these are the same. These are equal and bigger than smallest. You know, opposite the largest side in this one as well. These ones comparatively, here you compare these two using the triangle longest side theorem. Or something like that. Just, I don't know if it's specifically longest side theorem, but the way that they compared. One was compared to the other in that kind of way. I don't know. I'm trying to explain it the best I could. I did it with you there through some good old reasoning. Maybe an indirect proof did it. I don't know. Okay, that was kind of fun. All right, number 38, mathematical connections. In triangle DEF, I might draw this. Measure of angle, I will draw this. Measure of angle D is x plus 25 degrees. Just going to be a random just drawing here. DEF. Measure of angle D is x plus 25 degrees. Measure of angle E is 2x minus 4 degrees. And measure of angle F is 63 degrees. List the side lengths and angle measures of the triangle in order from least to greatest. Don't go by my drawing. I just made that thing up. Well, what we do know for sure is that all three angles in the triangle have to add to 180. So x plus 25 plus 2x minus 4 plus 63 equals 180. Let's solve for x, and when we plug in x, let's figure out how these angle measures actually compare. X plus 2x is 3x. 25 minus 4 is 21. Plus 63 is 84. And then we subtract 84 from both sides, and you get 96. Divide both sides by 3, you get 32. So measure of angle E is 2 times 32 minus 4, which is 60 degrees. And then you can do one of two things here. Either add these up and subtract from 180, or plug in this thing here. Measure of angle D is 32 plus 25, which is 57 degrees. And to compare 21, 23, yes, that would work out. So 57 degrees. So list the side lengths and angle measures of the triangle from least to greatest. So as far as angles, least to greatest, we're going to say D, then E, then F. And then opposite these sides are going to be ranking the sides here. So opposite D is EF. Opposite E is DF, and opposite F is DE. So DE is going to be the longest side, is opposite the largest angle right there, and so on and so forth. So these are the answers that we'd have there, from least to greatest. All right, number 39, analyzing relationships. Another triangle inequality relationship is given by the exterior angle inequality theorem. I don't know if I've seen this before. It states, the measure of an exterior angle of a triangle is greater than the measure of either of the non-adjacent interior angles. Oh, well, I know that when you add these together, it equals that one. That's a for sure. Explain how you know that measure of angle 1 is greater than measure of angle A, and measure of angle 1 is greater than measure of angle B in triangle ABC with exterior angle 1. Measure of an exterior angle of a triangle is greater than measure of the non-adjacent interior angles. Angles. Okay, let's go with this. Let's look at this drawing. Explain how you know. is greater than the measure of non-adjacent interior angles. What I'm curious about, what I'm looking into, they say exterior angles greater than these. What I'm curious about is if C is very obtuse right here, then 1 becomes very acute, but then I guess those become acute by comparison, right? So, okay. I'm going to first do some math stuff to base this thing off of and kind of see where I can go with it on the explanation. Measure of angle B plus measure, A plus B plus measure of angle C equals 180. And the measure of angle 1 plus the measure of angle C also equals 180. Therefore, these, by the transitive property, measure of angle A plus measure of angle B, I'm really going to hit what's called the exterior angle theorem, plus measure of angle C equals measure of angle 1 plus measure of angle C. They have to equal each other because they both equal 180. When I subtract measure of angle C, measure of angle A plus measure of angle B equals measure of angle 1. So what I'm doing here is I'm showing that when you add these together, they have to equal this third thing here. And since they all have to be positive or, something like that, I think that that's going to kind of conclude exactly what we're saying here. Because the two added together equal, because the two non-adjacent interior angles add together to equal the exterior angle, then the exterior angle must be larger than either of those two angles, right? Because those angles need to be, it needs to be larger than them. No angle can be negative. No angle can be 0. They're going to be positive, but then that has to be bigger than it that way. That's how I'm going to reason with it. It works with me. Hopefully it works with you. In exercises 40 and 41, describe the possible values of x. Oh boy, we're digging deep into here. So this time, I don't really know how the x's compare. I can make assumptions, but I don't think it's good to do so. So let's take a look, and don't go based off the drawing. The drawing could be whatever it is. Because if x is like 20, then clearly that's the longest side. But if x is like, you can't even be 1. If x is like 2, this is like the shortest side. So I don't know which one you can assume is longest and shortest and stuff like that. So I got a few things to compare. Let's do, and I'm going to put them in parentheses. Let's put x plus 11 and 2x plus 10 as the shorter sides. And let's make that greater than 5x minus 9. Like that. Now let's solve for x in this scenario. And let's make sure, so our big thing is we have to make sure that x is going to always be a value that gives us positive side lengths. And if it doesn't, then we have to nip that in the bud. So, I can work that out and figure out what the smallest then it needs to be, but we'll go based off the inequalities as a for sure. So x plus 2x is 3x, 11 plus 10 is 21, and 5x minus 9 is over there. Let's hope these pan out to be okay. Add 9 to both sides, subtract 3x from both sides, and then divide both sides by 2. You get x is less than 15. Hopefully you know how I flip that inequality when I bring this thing over on that side. That's what we're saying. So there's one thing. X is going to have to be less than 15 in one of my restriction cases. Now let's look at another restriction case. We'll keep doing some of the same stuff. Let's now look at x plus 11. Let's treat x plus 11 and 5x minus 9 as the two shorter sides. And make it greater than 2x plus 10. Let's see how this works out. X plus 5x is 6x. 11 minus 9 is 2. And here, if I subtract 2x and I subtract, I kind of like this problem as far as I applaud their setup in making these numbers so far be clean. Divide by 4, you get x is greater than 2. Okay. And let's do a third one. So now x has to be somewhere between 15 and 2. Let's see if that still works. Let's do a third one, and let's look at 2x plus 10 and 5x minus 9. I somehow don't believe that this is going to lead to positive values. I feel like these have to be bigger each time. I don't know. We'll check because they're all variables. Greater than x plus 11. Somewhere a restriction has to apply. 2x plus 5x is 7x. 10 minus 9 is 1. And here's x plus 11. Oh, this is going to break my fraction thing. So here's 6x and subtract 1. Make sure everything's good. Subtract 1, I get 10. And x has to be greater than 10 over 6, which is 5/3. X is greater than 5/3. Okay, So here's the thing. If x has to be greater than 5/3, but x also has to be greater than 2, 2 is more than 5/3. So the 5/3 one does not apply. Even if it did, I think 5 times 5/3 minus 9 might give me a negative number. I'm not for sure, but that one cannot apply in this case. So x has to be between 2 and 15 seems to be the case for this. And if x is 2, 5 times 2 is 10, minus 9 is 1. That can still work. So I'm going to go off that one right there and say x has to be between 2 and 15. Once again, 5/3 is less than 2. And if x has to be greater than 2 in one of my restriction things, then I have to stay... I have to constrict myself as much as possible. If there's a restriction there, I need to apply it if it's within that ceiling. Or within that range, I should say. That looks like number 40. All good there. All right, let's go to 41. And listen, let's do the same thing. It's more of the same. It's working itself out. Let's just go for the first two I see here. Let's look at 6x minus 11 plus 3x minus 1. And let's see what happens when it's greater than 2x plus 3. Okay, 6x plus 3x is 9x. Negative 11 minus 1 is negative 12. Subtract 2x from both sides and we get 7x. Add 12 to both sides and we get 15. And x has to be greater than 15/7. We'll just see what that is for what it is later. How it compares to keep things positive and if it is within a bigger restriction. Now let's look at 6x minus 11 and 2x plus 3 as the shorter sides, and let's compare that to being greater than 3x minus 1. I mean, if it's going by being drawn to scale, then the 6x minus 11 is going to be the longest side, so this might be a version we get to look at, though. So 6x plus 2x is 8x, and negative 11 plus 3 is negative 8. And then I get to subtract 3x from both sides, and I get to add 8 to both sides. I was applauding them a second ago about being all yeah, but now it doesn't. Now it's all yeah. Now 7/5 is 1.4. 15/7 is 2 point something. So this one's actually even more inferior when it comes to what it is that we can make happen. So we're gonna nip that one in the bud. Let's look at the last one, the one that seems to make most sense with respect to being the smallest sides, treating them as such. 3x minus 1 and 2x plus 3. Being greater than 6x minus 11. So let's see here what happens. 3x plus 2x is 5x. Negative 1 plus 3 is 2. And subtract 5x, I get x. And add 11, I get 13. So x has to be less than 13 in such cases. So right now it looks like x has to be between 15/7 and 13. And that's likely the case. What we need to make sure is that when I do 6 times, and I think it works, 6 times 15/7 minus 11, I still get a positive number. Because if you look at, so 6x minus 11 has to be also greater than 0. All of them have to be greater than 0, but this is one that threatens being negative by plugging in an x that's too small. Case in point, if I substituted 1 for x, that I'd get 6 minus 11, which is negative 5, and that can't work. So 6x has to be greater than 11, and x has to be greater than 11 over 6. Now, is 11 over 6 greater than or less than 15 over 7? 11 over 6 is less than 2. 15 over 7 is more than 2. So 15 over 7 is within the range of, if I plugged it in, which I could have tried, I just didn't want to deal with fractions, that it would still stay positive. So this seems to work out that x can still be 15/7 and be good. So 15/7 is the smallest it can be. Listen, it can't even be 15/7. I think that's even better for it. And it needs to still be less than 13 and maintain its inequalityness. But I did want to test all three. It's really kind of hard to judge things for what they are, just being x's, especially with big minuses like that in the way. Good to compare all three, and we got what we got. All right, number 42. How do you see it? Your house is on the corner of Hill Street and 8th Street, so it's right here. The library is on the corner of View Street and 7th Street, so right here. What is the shortest route to get from your house to the library? Explain your reasoning. Washington Avenue. Oh, here we go. Besides the diagram, Washington Avenue is the shortest route I can take to get from my house to the library. Now, as much as you want to say because it's a straight shot, I get it, but that even goes further into the triangle inequality theorem. The triangle inequality theorem would indicate that the distances for traveling across 8th Street and View Street, or Hill Street and 7th Street, must be greater than just traveling through Washington Avenue. See, this is the triangle inequality theorem at play. That the sum of two sides, boom, boom, must be greater than any third side, even if it's the longest side. So this distance must be longer than that, and then this distance must be longer than that if these are indeed triangles. And they are. That's just how the drawing is. Excuse me. So that's how 42 is. Not, it's a straight shot. But there's traffic on Washington Avenue. Yeah, I know. But this is shortest route, not shortest time. And time is not measured here. All right, number 43. Proving a theorem. Use the diagram to prove the triangle longer side theorem. Given this, prove that. It doesn't say indirect proof. I guess we're going more two-column proof with this thing. Wonder how good I am at using ones without numbers. I'm more of the side angle side kind of person with these. I don't know what it is that I'm going to prove that's going to work this one best. So I apologize if I don't get this down pat. Given BC is greater than, I don't know if I'm going to do too well on this one. BD is equal to BA. Now here's the thing. This is all math so far, unless we're doing, I don't think we're doing triangle congruence proofs and CPCTC and stuff like that. Measure of angle BAC is greater than measure of angle C. Now we're proving the theorem, which means we can't use the theorem in its proof, right? I don't know if we're allowed to use the other ones in the proof, though. It seemed like they did that for the indirect proof. It seemed like they were able to use the triangle larger angle theorem in it. I don't know. Let's see if we can come up with that. See, this is more one of those, I almost want to call these postulates. You know, it's almost, we should accept its truth for what it is and just, you know, be good with it. So, 1, BC, I'm just going to write out the givens. BC is greater than AB and BD is equal to BA. I was going to say true. Given. All right, so this one's marked. BD equal to BA also means congruence, but I don't really think we have to go with that. What are we trying to say? Measure of angle BAC. Where's BAC? This guy is greater than the measure of angle C. So eventually we're going to get into that whole triangle mess there. Okay, before I get more into that, I want to think about what I want to do with the proof itself. What we can do is we could talk about if these two sides are equal. What's the other one? BC is greater than AB. Where's BC? This? BC is greater than AB. Okay, so somehow we're going to be able to prove something about those things comparing to themselves. What we can do, I don't know. I'm going to kind of talk you through kind of this isn't even a plan. This is just what I have. If these two are equal, then that means that these two are equal in length, in measure, I should say. And then this will be 180 minus the sum of both of those two, and those would be the same. Now, this is also 180 minus that. Maybe the D can go and be a part of what we're going to talk about there, and D would therefore be the largest angle, and then I can work something out. I'm really not sure where I want to go with this proof. I can walk through this over and over, and there's just no guarantee that something's going to come to fruition. Let's work off that a little bit, use some transitive property stuff, and see where I can go from there. Measure of angle BAC is greater than measure of angle C. That's these two. So that's this length. Because this is the theorem, right? I haven't proved it before. So, all right, let's try it. Let's try and say measure of angle 1. Let's see, triangle. Don't write triangle. You have a symbol. Triangle ABD is isosceles. By definition of isosceles triangle. I know that I know that we might state congruence there. I'm going to just do equal measures if that's okay. So now I'm going to say measure of angle 1 equals measure of angle 2. Also, definition of isosceles triangle. Base angles of a triangle have equal measure. Base angles of isosceles triangle are equal measure. Okay, so equal measure. And I don't really feel like we're going to talk about... I want to know why I'm going to use 3. BD equals BA. Oh. Hold on. What are we saying here? Hold on. I don't know if I have to use the isosceles stuff. I'm sorry. Let me get this out of the way. Here's what I'm going to say instead. Okay. You know what? Keep it. I don't know if I'm going to use it yet or not, but with the isosceles triangle, these two angles are equal. Hold on. I lost how I'm going to use what I'm going to say with these two being the same. I can say that when I add this one to it, it makes this larger than that one. Yeah, that's fine. Okay, yeah. Okay, listen. There are one of two ways we can do this, and either should work. But this one actually uses measure of angle 3 this time, I think. If these are isosceles, that means these two angles are the same. But if I extend this side here, that would make this angle, therefore, greater than what they were before, because there's more to add into it. But I think I want to use this version of it because that's how it would work. So I now got to think about how I want to lay that thing out in its own proof in terms of saying measure, if these are equal, measure of angle 3 is an angle measure. Measure of angle 1 plus measure of angle 3 is greater than measure of angle 2 by angles have to be greater than something. You know, if I'm adding this measure of this angle in, it needs to be greater. I don't know how I can reason with that. I'm just going to say measure of angle 3 is greater than 0. That's not a measure. Measure of angle 3 is greater than 0. That's not really good theorem to say there. But with 5, measure of angle BAC, measure of angle BAC is equal to measure of angle 1 plus measure of angle 3. This is the addition angle addition postulate. And if measure of angle 1 plus measure of angle BAC can take this guy's place. So 6 measure of angle BAC is greater than measure of angle 2. I don't know if I can call that substitution or transitivity property. I'm going to call it substitution because I don't want to be wrong and call it transitivity, because one is an inequality, one is an equation. Now, I need to prove measure of angle BAC is greater than measure of angle C. Oh, I didn't notice that. Okay, that's still, I can still use that. I just don't know where I can go with it. C has this same, so check this out. C's side opposite, it depends on if you're looking at this or in the bigger triangle, and I assume the bigger triangle. In 2, this side opposite is bigger, and in C, it's even in a bigger triangle that's longer than it. This is something I can deduce talking to you verbally about it. I'm trying to think how I can say that I know for sure that C is less than 2's angle. Measure of angle C is less than measure of angle 2. How can I say that in their own, in a single statement? I don't know if I can. I feel like I'm walking through this proof in kind of an incorrect way. I reasoned with the wrong angles here when I did this. I don't want to shut it down, though, either, because I'm kind of along the path. If I can just show that 2 is greater than C, then I'd be good. Oh, you know how I can do that? We just had a theorem. What was it called? Exterior angle inequality theorem. Check out C. Check out 2. 2 is an exterior angle of the non-adjacent angles C and 3. So I can say that measure of angle 2, this will work. Measure of angle 2 is greater than measure of angle C. I knew I had some way to say it, and thank God we had that problem. Otherwise, I would not be able to say it. Exterior angle inequality theorem. I'm sure guys, there's so many ways you can probably do this proof. Probably shorter ways as well. The thing I'm afraid to use other theorems like this, but I'm really afraid to use the triangle longest side theorem. I don't want to use that if I have the triangle largest angle theorem in the way. Now this looks more like transitivity property. 2 angles, if one angle is greater than this guy and this angle is greater than that guy, then BAC has to be greater than C. Measure of angle BAC is therefore greater than measure of angle C. I'm going to call that transitive property of equality. That's not so much a substitution anymore. 2 angles greater than another angle is greater. One angle greater than another angle that's greater than that angle has to be greater than the other angle, kind of thing. Of equality. No, of inequality, really. I don't know if that's the name of a property then. I don't know if you call that transitivity property. I'm really bad at this kind of stuff. If A is greater than B is greater than C, then A is greater than C. I don't know what that kind of name is called, unless it's called transitive property of inequality. If so, I'm going with it. That concept makes enough sense. Anyway, guys, I'm going to leave it at that. Myself and proofs, not the greatest. All right, that was number 43, by the way. We're down here. Never said I'd be perfect with these, y'all. I am sight reading these as I go, clearly. Number 44, using structure. The length of the base of an isosceles triangle is L. Okay, let's make an isosceles triangle to work with what they're telling you. So this would be considered the base. The other are called legs. Describe the possible lengths for each leg. Explain your reasoning. So here's X and X. Keep in mind they'd have to be the same. Okay, so in an isosceles triangle, remember L could be the longest side, it could be the shortest side, it could be equal sides, but that's not something that we really compare. It says the possible lengths for each leg. If L is the shortest side, then L has to add with another X to be greater than X, which means L would have to be greater than 0, of course. I think we kind of saw this for another problem. This is a lot like another problem from before. So that's one possibility. And then also X plus X would have to be greater than L. So L would have to be less than 2X. So L is greater than 0, but less than 2X. So the way that we want to state that, I mean, the explanation is the math. By the triangle inequality theorem, there's my reason. L must be, and that's L, a positive value that is less than double the length of either leg of the isosceles triangle. Okay. All right, number 45. Your classmate, not a friend, but a classmate. Your non-friend classmate claims to have drawn a triangle with one side length of 13 inches and a perimeter of 2 feet. Is this possible? Explain your reasoning. Well, this classmate is going to fail. One side length of 13 inches and perimeter of 2 feet. Is this possible? No! This is not possible. Side lengths must be positive. So the sum of the side lengths of a triangle must be greater than any one side of the triangle. This is not only not greater than, it's significantly small. Oh, I'm sorry, 2 feet. I'm sorry. I thought it was the same units. Hold on a second. Let me go back. Guys, I'm really sorry about that. I'm like, what are they talking about? Okay, okay. So this is possible. Well, actually, hold on. Let's check. Let's check on this here. 13 and 2 feet. Okay, so oh, you know what? Yeah, this is possible. Um, let's check on this. I'm sorry about that. All right, 2 feet. You know what? Actually, this might not be possible. Oh, sorry about that. All right, let's have a side length that is 13 inches. And then you have some X and some Y. All right, X, Y. All right, X plus Y has to be greater than 13 or whatever other lengths we have. But 13 would be the longest side because this entire triangle would be a perimeter of 2 feet. X plus Y plus 13 equals 2 feet, which is 24 inches. So X plus Y, X plus Y would have to equal 11. Okay, 11 has to be greater than 13. 11 is not greater than 13. Okay, so no, it's not possible. I'm sorry about the initial thing. I totally did not read that. This is not possible. I should really just edit that out, but it was kind of funny, actually. The sum of X and Y would be 11 inches, which is less than the third side length. Now I can't assign this problem to my students because I can't have this part of the video on there, and this is messy diagramming. I don't even need this one that says 11's greater than 13. 11's not greater than 13. That reminds me of give him the stick. Don't give him the stick. Extra credit if you know what that's from. Cut 2 pieces of string. I'm probably not going to do that. Construct 2 pieces of string that are each 24 centimeters long. Construct an isosceles triangle out of one string and a scalene triangle out of the other. Measure and record the side lengths. Classify each triangle by its angles. I'm not going to do that, but what I will do is I'll pretend I'll do a compass construction. This isn't quite what the problem says to do. What I'm going to do is a compass construction. I will put this thing at 240. I'll call that the equivalent to 24, right? 240 is the same as 24. I'm going to put a dot somewhere, boom, like that, and I'll pretend like I can draw a string anywhere. I can place 2 strings anywhere along this arc right there. Okay, so as long as it's from the dot to there, then it makes string lengths of the 24 centimeters. So I'll make one in, say, blue here that goes like this, because that'll be 24, and that'll be 24 like that. Because I'm not going to cut a string. I don't even know if I have a string with me. So right there. So this is 24 centimeters, 24 centimeters. So those are my 2 strings, and then there's this unknown. Then I'm going to do another one. Let's make it green, say. And this will also be 24, and this will also be 24 like that. Okay? So 24 and 24, and then this other side length like that guy. All right, 24. Whoops. All right, so let's call that Y, and let's call this thing X. Okay. Measure and record the side lengths, then classify by its angles. Ooh, that's cutting it pretty close to a right angle on that thing. This is going to take a few measurements here. Here's the problem. Wait, where's my little protractor or compass? Okay, I'm going to measure it by the compass. The problem was I measured these by those widths. So I'm just going to measure it this way. So this guy stretches out to, oh, it doesn't go far enough. Oh no. You know what? Forget it. You guys can do it. You can measure it. I can do the smaller one. Here, let's put these at these lengths here, 280. So I'll make it 28 centimeters. Is that okay? All right, it's going to that length. It's like doing the splits. I don't know if that works right when we say that, because I don't know what these numbers are, the 280 number itself. I assume that number has to do with width, because that's not degrees, because that'd be 180 if so. So I assume that's a width thing. So, okay, well, I'll call X then 28 centimeters. I guess that's how that's going to kind of work. But now it's acute, right? So, acute. I was going to try and make it possibly right or obtuse, but I guess it's not anymore. This green one's also clearly acute. Right there. Now, what is Y? I probably could use the ruler tool, but it just takes too long for me with the rotating it. So, sorry about that. This is going to be about 127, so I'll call it 12.7. 12.7 centimeters there, which is also clearly acute. Now, I just know these are clearly acute just based on the nature. Obviously, this one's super small with that kind of weight. These are going to be less than 90-degree angles. They have to be. And this one very close to equilateral. Being isosceles, it's also going to be very acute. So sorry, I wanted to make something different. Just can't. Number 47, prove the triangle inequality theorem. Okay, we'll have 3 more problems, and that's a proof, and that's a proof. That one's an indirect proof. I forgot about those. I clearly won't have enough room to do a proof over here. I don't know if I know how to prove the triangle inequality theorem, but let's give it a shot. That's a lot of things to prove. Maybe I get to use that other thing before. I don't know how to prove it. Let's try it. Here we go. It just says given triangle ABC, literally. Statements, reasons. Now, I believe I'm allowed to use, if it serves any purpose, I believe I'm allowed to use the largest angle side theorem, largest angle theorem and longest side theorem, things like that. So, I don't know where to begin with this one. So here's triangle ABC. Because I might have to draw things. Now, all of them would be the same proofs in and of themselves with different letters as far as the, once I prove one of the things, I think I can repeat the concept of the proof in other places. AB plus BC has to be greater than the AC, etc., 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 right? They have to be greater than the other side. So let's do it for one of them, and then see if I can just replace letters through a copy-paste format. Now, what am I going to do with this? AB plus BC has to be greater than AC. Okay, well, based on the way that I drew it, I'm going to change that. So let's do AB plus BC is bigger than AC. Okay, so I think what I'll do, I'm wondering what would happen if I drew an altitude. I'm thinking about right triangles. I'm thinking if I drew an altitude, and this isn't necessarily a perpendicular bisector, but it would be perpendicular. But if I drew some BD, my thought to this is, AB has to be greater than AD, and BC has to be greater than DC. Therefore, AB plus BC has to be greater than AD plus DC. That works. All right, let's do that. Yeah. So, I mean, this I have to say more, but I'm going to draw BD, draw altitude BD, excuse me. Altitude BD. Now, listen, I only want to do this once. I don't want to do it 3 times. It would be the same thing the other 2 times through drawings. Maybe there's a way you can shorten it once you know the others. I don't know. I don't really want to get into that. If that's okay, I'm just going to do one of them. So draw altitude BD, construction. So it's a construction thing. Okay. So with that altitude, now we can say we have a couple right triangles here. So, or right angles. Angle ADB is a right angle, and angle CDB is a right angle. By definition of altitude. I don't know if they say draw altitude or draw BD perpendicular to AC. Let me say it like that. I'll say draw BD perpendicular to AC. And definition of perpendicular lines. Because I just said draw an altitude. We didn't say which way it went. With that in mind. Plus, I'm trying to think if when doing an altitude, what if it was an obtuse triangle? I wonder if this Pythagorean theorem concept still flows. I guess so. For my drawing, it does. So I'm going to go with it. So triangle ADB. I should have said they're both right angles because I'm going to say this time. Triangle ADB and triangle CDB are right triangles. That was a lot faster to say that one by definition of right triangles. Okay. Now, with that in mind, if they're right triangles, AB is a hypotenuse and BC is a hypotenuse. AB and BC. Let me so time out. Here's what I was gonna do. I was gonna say by Pythagorean theorem, those things were greater. I think here's where we can use that other theorem. I don't even know if we have to say the right triangle part for this anymore, to be honest. I think that something being a right angle would automatically be the largest, but maybe we should say it in a right triangle as well. Was another one a theorem where we said that, or did it just say explain how you know that it would be the largest? Let me check. We were looking at the hypotenuse. Explain. Okay, they didn't say it was a theorem. It just made sense. So this one here, I'm getting at the fact that AB would be larger than AD. So AB, the length of AB is larger than AD, and BC would be larger than CB would be larger than CD, or BC larger than CD by the triangle largest angle theorem. Because we're using that theorem for this inequality theorem. Okay? So if those are larger there, then we could say that AB, I don't know how to use this reason. It just makes sense. But AB plus BC has to be larger than AD plus CD by the bigger sides theorem. Two sides longer than shorter sides when added together are bigger than. There's something, maybe I can use a substitution here. I'm not really sure what it is. But math, boy, I don't know how to do that. It's you know what? It's a little addition property of inequalities. I don't really know how to reason that one. Hopefully you can tell what I'm saying. These two are already larger than these two guys here. Therefore, when added together, they must be larger than those two guys. I don't know how to make that reason. I apologize for that. Now, what I need to say is that AD plus CD equals all of the AC. I probably should have written the AD plus CD differently. That's segment addition postulate. Now, by substitution, AB plus BC has to be greater than AC. So you can see why I don't want to write this one over and over. But AB plus BC, and I had a wrong reason probably for that one. And I'll just call that substitution. I don't want to make the mistake on anything else. Substitution property. All right, so there's that one. That's the concept of it. I'm sure you could do it in all the different ways, and I'm not going to do all three. Even if I copied, pasted, changed the letters, I'd have to redraw it as well, and I don't think it's worth the hassle. So that's my concept of it, guys. When breaking up this altitude, these sides are going to be shorter than these. You could always use Pythagorean theorem to work that out. And I think that's one that I would use that would be, maybe I could reason this one a little better when I said it. But yeah, that's how I worked it. All right, two more questions. We got number 48. Number 48, tending to precision. The perimeter of triangle HGF must be between what two integers? Explain your reasoning. Can I not undo that? What happened? Okay. So Interesting. So triangle HGF here, we see these side lengths, and these are the smaller sides among all these, right? So, this is the, well, I don't know if that's the most obtuse, actually. You know what? We don't know anything about anything necessarily there. Yeah, they're drawn to be super obtuse, but let's come up with the possible values of x, the possible values of y, and the possible values of z based on this. No knowledge of anything else with these things, unless maybe I should assume something based on manipulation. I don't know. I think the way that these angles can bend any which way. We just don't know. So let's look at what x can be. If x was among the smaller sides, x plus 3 would have to be greater than 5. So x would have to be greater than 2. However, if x was the longest side, 3 plus 5 would have to be greater than x. So x would have to be less than 8. So x has to be between 2 and 8. So let's keep those in mind. Now, let's kind of change colors in all these things. Let's make y like green, and let's make z like purple. Okay, so for y, let's compare 3 and 4. Y plus 3 has to be greater than 4. So y has to be greater than 1. And 3 plus 4 has to be greater than y, which is 7. So y has to be less than 7. So y has to be between 1 and 7. Now, I feel like I'm not going to answer something perfectly. By the way, these aren't answers. But I feel like I have to be stingy about how I work some of these things out because of how it changes different values. And we'll see how I have to work out my final answer. I'll tell you what I mean with that in a second. If z was the one of the shorter sides, z plus 4 has to be greater than 5. So z has to be greater than 1. And then 4 plus 5 has to be greater than z. And so z has to be less than 9. So z has to be somewhere between 1 and 9. Now, one other thing that I'm going to do before I get into anything else is that, because here's the thing, maybe we're talking about the shortest perimeter could be 2 plus 1 plus 1, and the greatest thing can be 8 plus 7 plus 9. I don't know if that's necessarily true, because I don't think that would therefore make x or y some of the longer side. If these lengths are the way they are, I think it changes the way that those lengths mold. Meaning, if this stretches 5 and 4 the way that it appears, if this 5 and 4 stretch out like this, that would make z incredibly long and closer to 9, but it would likely shrink y in the process. You know what I mean? And I don't know how far they go with integers, but here's the other problem. Adding 2, 1, and 1 to get 4 also is not allowed because 2, 1, and 1, you can't make a triangle out of 2, 1, and 1. You can't make a triangle out of 2, 1, and 1. So the perimeter can't even be 4. One of these would have to be bigger to make that so, but maybe that works out still. The perimeter must be between, so I'm going to say this first and then see if we can shrink it any more, but the perimeter must be between, now I'm going to do 1 plus 2, 1 plus 1 plus 2 is 4. So 4 and perimeter, and then 8 plus 7 plus 9, I think it's 24, and 24. So right now I'm going to put that as the answer. I'm dubious about that, but I don't know how I can shrink it much more either. You know? Because the problem is how things would change other things. If x is going to be a super long side, it would shrink how much y and z could go, but I don't know by how much. Well, I think we can shrink it. Let's put it this way. If z, let's put it this way. If z was the longest side, the longest it could be is 9. I mean, it can't even be 9. But the longest it would be, ideally, is 9. X and Y, when added together, need to make sure that they are less, or are more than the, oh wait, they'd have to be more than the 9, not less than the 9. Well, they'd have to be more than 9. You know what? I'm going to leave it like that. I might be missing some stuff. I know I'm missing some stuff as far as we should be able to restrict it more. There's no way it could be 4. Right? It just couldn't be 4 with the way that these things are 5, 4, and 3. They couldn't be the shortest. I mean, it can't be 4 literally, but it couldn't even be 4.1. With these being what they are, they couldn't be the shortest together at the same time. And I'm just thinking about how that changes. And I don't know how to put that. And I feel I should. I feel I should. And these can't be all 8, 7, and 9 together. I feel like they can't all be 8, 7, 9 together. They would just be too long. They can't all be longest sides at the same time. But then I don't know how short I can make it. So I'm just going to leave it between 4 and 24. It clearly should be more restricted than that, but it clearly also can't be those values. I think that's the better thing to mention. All right, last one, proof. Write an indirect proof that a perpendicular segment is the shortest segment from a point to a plane. Okay, well, that's an important thing to mention. Let's see how we can do the indirect proof. We have to prove that PC is the shortest segment from plane P, from P to plane M. So first, good, I get to type. First, let's assume, temporarily, that PC is not the shortest distance segment from P to plane M. Okay? First, let's assume it's not the shortest distance. The way that I want to kind of talk about this, I mean, I don't know if this is going to be perfect how I say it, but the shortest distance from any point to a plane is the segment that is, there are two different words. You say perpendicular. Yeah, perpendicular is the one I say. Perpendicular to that plane. And PC is already perpendicular to it. I don't know if I'm reasoning with that correctly. Can I use that definition in its reasoning? No, let's do this. We can't use this definition. That's the whole point. They want to say, sorry, prove that a perpendicular one is. Okay, so hold on. Let's do this. I'm going to draw another thing. I don't know if that kind of works, but I'll just call this D. Okay. Let's assume that it's not. So now let's draw another one. Drawing another segment, PD, that is not perpendicular to M, can create a triangle. There we go. Can create a right triangle. And I'll use that triangle symbol that I had before. I don't know if this is the way that you do the proof, but it's going to work out for me because we get to use exactly what we were talking about before. Where's my triangle symbol? Triangle DCP, where C is the right angle and PD, segment PD, is opposite angle C. By the triangle largest angle theorem, I believe it's called. Largest angle theorem, PD is the longest side of the triangle because it is opposite the largest angle. Therefore, PD is greater than PC. So PD, therefore, I already said therefore. So PC is the shortest segment. So basically, any other segment that's not perpendicular will be longer. That's what I'm saying. Any other one that you do will be longer if it's not perpendicular. Is the shortest segment from P to plane M. And all I'm going to do from here is I'm just going to be putting in some segment bars. Segment bar, PD, segment PD is the longest side. I got to keep those ones the same like that. PD and PC like that. All right, I think that's gonna work. Okay, guys, that's the last one. I think that one worked out for itself, and that ought to do it. This is Mr. Robinson. Thank you so much for watching. Make sure you check everything down below that you need in case you want to go back to them, timestamps and all. Thank you so much for watching, guys. Take care. This was fun and different for me, the indirect proof stuff and kind of dancing around some of those other two column proofs. But thank you, guys. Take care. I will see you in the next one.